And with this chapter, we're going to get a little bit into radiometric decay and how we absolutely date things. There is a little bit of math involved with this, but try to stick with me. If you still feel a little bit hazy about it at the end, never hesitate to send me a message in Canvas. But just some review of things we learned earlier on in the semester. When we look at our atoms, it's made up of 3 different particles: our protons with a positive charge, electrons with a negative charge, and neutrons that are completely neutral in charge. And we care about 2 things about our elements. The first is its atomic number. The atomic number identifies each element. So for example, carbon has an atomic number of 6. Nitrogen has an atomic number of 7. If we know the number, we know which element we're dealing with. But knowing the atomic number also tells us how many protons are in the nucleus. When I'm looking at carbon, because it has an atomic number of 6, it has 6 protons. If we add another proton to it, it will no longer be carbon. Instead, because it has 7 protons now, it'll be nitrogen. But in addition to the overall charge of our atom, we care a lot about the mass, or the weight and size of the atom. Remember that electrons have almost no mass. Almost all of the mass of an atom is contained in the nucleus, where those positive protons and neutral neutrons are. So in addition to our atomic number, the second thing we care about with our atom is the mass number, or the atomic mass. And this is the number of protons plus the number of neutrons. All of the particles that have mass or weight to them, this number will tell us the atomic number, or the atomic mass. But we'll see that some elements have differing masses. They have differing numbers of neutrons inside of their nucleus, so some are a little bit lighter weight than others, and others are a little bit heavier, even though they're all the same element, because they have the same number of protons in the nucleus. It's the number of neutrons that are changing and affecting the mass number. But some elements are unstable. The majority of the atoms that we interact with every day are stable. They don't change over really long periods of time. But some isotopes are unstable. They're held together with bonds that aren't really strong enough to hold the nucleus together. So sometimes it will decay and break apart and kind of eject a piece or a particle from the nucleus. And all of this is called radioactive decay. It's just where unstable atoms break apart in an attempt to become more stable, and it releases energy when this happens. We have 3 different types of radioactive decay on our planet. The first one is called alpha emission, and this is where an unstable atom releases 2 protons and 2 neutrons from its nucleus. And this alpha emission is going to change both the mass number and the atomic number. It's going to change its mass and charge. Because we're getting rid of 2 protons, we are getting rid of 2 positive particles. It's going to reduce our atomic number by 2. But we're getting rid of 4 particles that have mass, so it's going to reduce the mass number of this atom by 4. Our second type of radioactive decay is called beta emission, which is shown here in the middle. And this one's a little bit different because we actually see that it's a proton and an electron combining and forming a neutron. So here the mass number is going to stay the same because we're not changing the mass. But instead we're going to see that the atomic number increases by 1. And then our final type of radioactive decay is called electron capture. This is where an electron is captured by the nucleus and combines with a proton to form a neutron. So here we again see that the mass number stays the same, but now our atomic number, the number of protons, is going to decrease by 1. So when we're looking at how these isotopes radioactively decay over time, we see that it's usually not just one step. It's going to be a series of transformations or decays that's going to go from an unstable atom to a stable atom. So we need to be able to differentiate which one is the unstable, which one is the more stable, which one is it decaying into. So we call the original atom the parent isotope. This is the one that's totally unstable and is either going to let something out of the nucleus or capture something. But the slightly more stable isotope is going to be called the daughter isotope. So this is the one that results from the radioactive decay, the one that is slightly more stable than the original parent isotope. Radiometric dating is going to be very different from our relative dating. With radiometric dating, this is an incredibly reliable and accurate way to calculate an exact numerical age for a rock. And the reason why it's so reliable is because the rate of decay, the amount of time it takes for a parent isotope to decay into that daughter isotope, never changes. And we've been able to very precisely measure that rate of decay for lots of different elements. So as long as our daughter product, that slightly more stable product, has been accumulating, we can figure out an exact date or an exact age for a rock, or an age in which a number of years in which have passed since it formed. And we do this by something called the half-life. And the half-life is the amount of time it takes for one half of those parent isotopes, the original unstable ones, to decay into the more stable daughter isotope. So again, just the amount of time it takes half the parents to decay into daughter isotopes. So we see that one half-life has passed when the amount of parent and daughter isotopes are equal to one another. So it's 50% parent, 50% daughter. But after each successive half-life, the remaining parents, we're going to see that half of them are going to decay into daughters. But if we know the actual half-life of an isotope, say how many years does it take for carbon-14 to decay, and we know the ratio of parent to daughter isotopes, then we can calculate an exact numerical age. And you'll be doing this a bit in mastering geology, so hopefully it'll become a little bit more familiar. And I don't like to ask math questions on the exam, so don't fret too much about this. So overall, there are hundreds of different radioactive isotopes. But in geology, there are 5 really important ones. 2 of these are uranium, which we can use for nuclear power. We also have thorium, rubidium, and potassium. But you'll notice that most of these half-life values, again, the amount of time it takes for half the unstable parents to decay into that more stable daughter isotope, you'll see that most of these have really long half-lives, where we're talking about hundreds of millions, if not billions of years, for half of those isotopes to decay. These will be really good at figuring out exactly how old the Earth is, or when nearby planets formed. And of course, geologists have tried to go out and radiometrically date the oldest materials on our planet and within our galaxy. And so far, they've been able to find rocks on every single continent that's at least 3.5 billion years old. And the oldest rock they found so far has been in Canada, and it's about 4.3 billion years old. And remember, we now believe that our Earth is about 4.5 billion. So we're really close here with rocks that we've been able to radiometrically date and accurately date. But you might have heard about a very different radioactive element called carbon-14, especially if you're into like Native American history and early humans. Carbon-14 is the isotope that we use to date very recent events. We wouldn't want to use it to date something that's 1 billion years old, but we would want to date something that's maybe 10,000 years old. And that's because the half-life of carbon is relatively short. On our last slide, we saw that some of those elements had half-lives of billions of years. But the half-life of carbon is only about 5,000 years. So it's really good at helping us date events from human history because it's present in all organisms in very small amounts. So basically, if I find any kind of plant or animal organism from the last maybe 50,000 years, I can use carbon 14 to very accurately radiometrically date it.